Welcome back to my new series, How It All Started LLM Edition. In this series, we are tracing the path to our current LLMs by reading the papers that built them. Today, we are going to talk about paper 3, Scaling Laws for Neural Language Model. This came out in 2020. Now, let's recap for a bit. Paper 1 gave us the architecture, the transformer. Paper 2 gave us the pre-training thesis. Feed a big transformer a huge web corpus, train it to predict the next token, and task behavior starts to emerge. Zero shot, before even instruction tuning existed. Paper 2 left us with a very specific line at the end. All models still underfit web text. Held out perplexity has as yet improved given more training time, which means the more we scale, the more improvements we are seeing. So we have not hit a wall. And that line is our on-ramp to paper 3. Underfitting is still a bottleneck. How do we scale the model? And paper 3 asks this question: how exactly can we write down a formula for scaling? That is exactly what scaling laws are. These are predictive relationships between model size, dataset size, compute, and test loss, fitted from a large grid of training runs. Let's get into the abstract. The line that we discuss is we study empirical scaling laws for language model performance on the cross entropy loss. What does this statement mean? First, let's define empirical scaling laws. Empirical means measured, not guessed. A scaling law is a relationship. What happens to performance as you grow things? So empirical scaling laws are relationships they found from a large grid of real training runs. Second, language model performance. Now, performance here has a precise meaning. How good the model is at guessing the next token. The score for that is loss, lower is better. And the third one is cross-entropy loss. Cross-entropy loss is the name for that score. How surprised the model is by the correct next token. Confident and right is a low score. Unsure or wrong is high. We'll get into it properly in section 2. Now, if you put the three together, and the finding is simple: make the model bigger, feed it more text, or spend more compute. And this loss drops in a very predictable way. So you have three power law curves where doubling one thing shrink the loss by a fixed percentage every time. So that is the whole paper in one sentence. Everything else is how they measured it and how to spend a fixed compute budget. So now we reach the introduction. The intro says that they will sweep model size, data, and training setup across many scales and look for smooth laws that they can write it down. That's chapter 2 done, the setup. Quick recap. They trained a whole grid of models across many scales, so nothing here rests on a single run. Next, what they found before they explain how. Now, this brings us to the summary. Two parts: qualitative takeaway and the actual power law. Let's take 1.1 first. Section 1.1, qualitative takeaways, and section 1.2, the actual power law formulas. Now let's take 1.1 first. 8 claims. Before we get into them, I want to spend a little time on some basic concepts you need in your head to make the sense of it all. The first one is convergence. Picture baking a cake. At some point, more time in the oven stops making it a better cake. It's done. Leaving it in longer, you're not improving it anymore. You're just burning it. In machine learning, convergence is that same point. Your model has squeezed pretty much everything it can out of the data with the setup you gave it. Keep training past that point and performance stops moving. It's peaked. Now hold on to that concept. The second concept is the power law. A power law means when one thing doubles, the other thing changes by a fixed percentage every time. It's not a fixed amount, it's a fixed percentage. Now the main idea of the paper is exactly one such number. Double a language model size and its loss falls about 5%. If we plot that on a chart, we will get a straight line. Left, you see the ordinary axis, and the line bends, the log-log axis, and it's dead straight. Straight line on log-log, that's the fingerprint of a power law. Now with these two ideas in head, let's weave that into what the paper actually cares about. The team found that the three things matter for a model's performance are model size, data size, and compute. Other choices turned out to be far less important. Depth, width, and attention heads. These are what we call as shape knobs. Now, model size is how many parameters the model has, roughly how much capacity it has to represent patterns. Bigger model, bigger brain. Dataset size is how many tokens it is trained on. And then there is compute. Compute is the trickiest of the three. Now, training happens in repeated steps called optimization steps. In each step, the model processes a batch, guesses the next token, checks how wrong it was, and nudges its parameters a little. One full pass through the entire dataset is called an epoch. But compute isn't about whether you have finished the dataset once. It is about how thoroughly you use that data to train a model of given size. More compute means more optimization steps, more opportunities for the model to learn, refine what is already picked up, and adjust its enormous number of parameters. Now, model size also fits directly into the cost of each step. A bigger, more complex model means every single step costs more work because there are more parameters to update. Same data, same number of steps. A larger model still takes more compute to get through it. So compute is really both of these multiplied together. How expensive each step is and times how many steps you run. That's the model size and size folded into one number, total work spent. Now we know all of the vocabulary: convergence, power law, model size, data size, and compute. Let's see what the paper actually found when they measured all of this. Now, this is figure one. This is main part of the whole paper. 3 panels. I'm going to go left to right. This is the test loss against compute, against dataset size, and against parameters. Every axis is logarithmic, and all 3 are the same thing: a straight line falling for 6 or 7 orders of magnitude. It means performance depends on scale, not shape. Grow model size, dataset size, and compute, and performance improves predictably. Depth, width, attention heads, they are second order. They barely move the needle. Loss versus model size versus dataset size, and loss versus compute. Each one draws that same straight line we just talked about for 6 or 7 orders of magnitude, from models with under 1,000 parameters to 1.5 billion. It's a big range, the same straight line. How loss decreases over training looks about the same whether you are training a small model or a massive one. The rate of improvement follows a very similar shape, regardless of the model's specific size. That means researchers don't need to train for weeks or months just to find out if a run is going to work. They can train for a short while, look at the early part of the training curve, and get a read on its long-term potential. Essentially, they are able to extrapolate predictably. That saves an enormous amount of time and compute. 4. Convergence is inefficient. Now, this is quite interesting. Say you have a fixed compute budget, which most companies would have that. That means you can only afford to run training for so long or with so many machines. But you're not restricted on how big your model can be or how much data you can use. Now look at the board. Same compute budget on both sides. A is a small model trained all the way to convergence. Its loss curve has gone flat. It means any more training is not going to yield any more results. B is the big model, stopped early. Its curve is still falling when we cut it off, and it's already below A's. That's the discovery. With a fixed budget, a very large model stopped short of convergence wins. It is better to train a bigger model and not wait till convergence than a smaller model which can learn smaller patterns and where you can train till convergence. Compute is model size and data multiplied together. The exponent is about 0.27. 10 times the compute needs less than double the data. The other 5x of growth grows into the model. So which means the bigger the model, you don't need as much data. Data requirements grow relatively slowly. Okay, 8 findings, no formulas yet, and that is a lot to hold at once. Take a breath. Chapter 4 turns all 8 into formulas, and honestly, the formulas are the easier half. Section 1.2 is where the authors turn those 8 findings into actual formulas. We're not going to map out every equation on this page. Instead, let's understand what the authors are actually trying to achieve with all this math. Now, it comes down to 2 things: prediction and optimization. Prediction means these equations let researchers forecast how much its test loss drops if they make it bigger, feed it more data, or throw more computing. It's a formula for forecasting AI improvement before even you build the thing. Optimization, on the other hand, means that we can predict performance, so we can work backwards. Given a fixed budget, the math tells you the best way to split it. How much should go into the model size versus data versus training time? The payoff is financial. Training a frontier scale model can cost millions of dollars. These equations let our lab run small, cheap experiments, fit the trend, and forecast what a run at massive scale will achieve before committing a budget. So essentially, a huge financial bet becomes a predictable one. 4 chapters in, we know the loss drops predictably. We have the formulas that say by how much. And still, nobody has told us where those numbers came from. That is chapter 5. On to the approach section. It opens with backgrounds and methods. And this is where the paper defines the loss this whole time. First, let's talk about the data setup. Web text 2 is the same family as the web text from paper 2. Remember the Reddit curated web corpus. Web text 2 is the big version of it. Second, tokenization. Same byte pair encoding from paper 2, where we said when a model sees unbelievable, it breaks it down into unbelief plus able. Again, same idea here with a fixed vocab with little over 50,000 possible tokens. Click on the link below for part 2.